Welcome to grade 12 advanced functions. Today I'll be teaching you 1.1 power functions. So the topic of this unit is obviously power functions, and the goal of this lesson is I understand what a power function is and can identify key characteristics of polynomial functions and their end behaviors. So this is just a simple review of a polynomial expression. We got y equals 3x squared plus 12x plus 9. So x is obviously the variable of this expression. 3x squared and 12x are the coefficients, and they are 3 and 12. The degree of this function is 2, since the greatest power of x in this expression is 3x squared. The leading coefficient of the function is obviously 3. And the constant term, which is a term without a variable, is 9. So some previous, if you need to refresh your memory from previous concepts from previous grades, these are some websites you can use. We got Khan Academy, ca.ixl math. These are specific links you could go to and kind of refresh your memory, I guess. And yeah. So in previous grades, you probably learned about linear and quadratic functions since they're the most common encountered ones. But in grade 12, we start going beyond that. So the definition of a power function is a single term polynomial function. For example, f of x equals 2x to the power of 3 is an odd power function. This is a single term polynomial function. This is also a single term polynomial function, but this has an even degree, which means it's an even powered function. So some names of polynomials by its degree would be this. So a degree of 0 would kind of be called a constant. When a function has a degree of 1, it will be called a linear function. Degree of 2, quadratic. Degree 3, cubic, and so on. So an example I could give you for a linear would be y equals x. Quadratic, y equals x squared. Cubic is y equals x to the power of 3, and so on and so forth. Y equals x4, y equals x5. Moving on, we got two graphs here. And in the first graph, you could see that it has a parabolic shape. You could assume it's a quadratic function because of the parabolic shape. So a quadratic function has a degree of 2 as stated here. So that means this is an even degree function. The second graph, on the other hand, doesn't look like it has a parabolic shape. Almost looks linear. So you can assume that this is an odd function. But as you can see, as this function heads towards the x-axis, you start notice that it's getting flatter, which means it's a higher degree. So it won't be linear. It would be possibly a degree of 3, which is a cubic function. So since it has a degree of 3, this is an odd degree function. So to better help your understanding of what I meant by it keeps getting flatter as the degree increases, I did this on Desmos. So this graph right here, the one that's parabolic, is indeed y equals x squared, while the one that gets flat towards the x-axis is y equals x to the power of 4. So what I meant was, as the degree gets bigger of a function, it starts getting flatter towards the x-axis, as you can see right here with y equals x4, rather than y equals x squared, where it's just a parabolic shape going up. I apologize for the faded words, but I'll try explaining this. Hopefully you guys can see. So moving on to end behaviors. So you might be wondering what an end behavior is. End behaviors are when we want to know what happens to the y values of a function as the x values head off to a positive or negative infinity. You guys might be confused, but I'll explain. So you might be wondering of how you would describe the end behaviors. So for a positive function with an even degree, I'll give you an example. So say something like y equals x to the power of 4. So the end behavior is as follows. So as x goes to the positive infinity, so as x goes to positive infinity, y would also go to positive infinity, since as x goes down here, and this has a parabolic shape to it. As x goes to positive infinity, y also goes up to positive infinity. And as x heads to negative infinity, so when it goes right to left, as you can see here, it still managed to go up. Y still increases, so y goes to positive infinity. So if you're talking about quadrants, from which quadrant it goes, it would go from quadrant 2 to 1, as normally when you look at a graph, it's always from left to right. So this is quadrant 2, it's quadrant 1. Moving on, for a negative function with an even degree. So say same function, just with negative in front. Y equals negative x to the power of 4. So this would obviously be reflected. So let me just draw a separate graph here, a mini sketch. It would be something like that. So as x goes from left to right, so to positive infinity, y goes to negative infinity. As you can see right here, it's in the negative area. So it's negative. And as x goes to negative infinity, so this way, from right to left, it also goes negative since they're both heading down. And if you were to write this in quadrant, it will go from quadrant 3 to quadrant 4. Alright, so moving on to odd degree functions. So for a positive odd degree function, I'll just give you an example. So y equals x cubed. I'll just give you a graph also so you can understand the end behavior better. So it looks something like this, going from quadrant 3 to 1. So as x goes to the positive infinity, as you can see here, y also goes to positive infinity. As x tends to go to the negative infinity, so from right to left, y goes to the negative infinity, as you can see right here. So if you were to write it in quadrant form, it would go from quadrant 3 to quadrant 1. And so now for an odd degree with a negative odd degree function, so I'll give you an example right now. So y equals negative x cubed, and if we're to draw a rough sketch for you, it will look something like this. This is going from quadrant 2 to 4. So you can see as x goes to the positive infinity, y goes down to the negative infinity, and as x goes to the negative infinity, y goes to the positive infinity, as you can see right here. And if you were to write this in quadrant form, you would see that it goes from quadrant 2 to quadrant 4. So now moving on to range. So the range for an even degree function with a positive leading coefficient is y is greater than 0, y equals all real numbers. So if you look here, you can see that this is an even degree function of 2, and it goes up. It's not below 0, so it obviously makes sense that y is greater than 0 at all times, as it doesn't go to negative. That's what it means when it says the even degree function with a positive leading coefficient is y is greater than 0, which is this. As on the other hand, for a function with a negative leading coefficient, it would have a range of y is less than 0, y equals all real numbers. So kind of similar to this graph, but it has a reflection on the x-axis. So it goes downwards and there's no positive y values, only negative. So you would say, as it said right here, y is less than 0, y equals all real numbers. So now moving on. So the range for odd degree functions with both positive and negative leading coefficients is y-ER, y equals all real numbers. As you can see right here, this is an odd degree function with a positive leading coefficient, as it's going from quadrant 3 to quadrant 1. You can see it has negative y values and positive y values, and it keeps going. So you would write y equals all real numbers. And this is one with a negative leading coefficient. As you can see, it goes from quadrant 2 to 4. So it has both positive y values and negative y values. And so you would write y equals all real numbers. So moving on to symmetry of power functions. So for a power function with an even degree, there will be a line of symmetry which reflects both halves evenly. So if I bring this graph back up, if I were to draw a line at the center of the graph, you can see these two sides are split evenly. You could tell it's a function, so you would know this is an even degree function. On the other hand, for an odd degree power function, there will be a point or rotational symmetry at the origin, which if rotated, both sides would be symmetrical. So if I bring this graph over and I put a point symmetry at the origin, you can see it's still symmetrical. If I were to rotate it, if you were to rotate this graph, like I'll just show you here, if I rotate it with the paper, it's still symmetrical either way. Looking at it from all different point of views, it's still symmetrical. So you'd know that this is an odd degree power function. All right, so now moving on to examples. Example number 1. What is the name by degree for the following polynomials? Don't mind this, I made a mistake. Let's put a question mark here. And what is the degree? So this question is asking you for the name by degree of the following polynomials, and you should also state the degree. So question A. In your notes, you would see I gave you this sheet which gives you the names of the polynomials by its degree. So using this sheet, you can use it to help you. So as you can see here, has a degree of 3, and you look back at your sheet, the one with the degree 3 is cubic. So you would write, so for A, so it would be by, so it would be name by degree is cubic, as stated right here. The degree of 3 is cubic. So you know degree is 3. All right, so now for B, 7x, you can see that the degree is 1. So you look back here, degree 1 is linear. So you would write the name by degree is linear. And since it has a degree of 1, degree is 1. All right, moving on to C, the final one of this example 1. You can see that it has a degree of 4. So if I look back at the sheet, degree 4 is quartic. So you know the name by degree is quartic. So you would write name by degree is quartic. And you can see it has a degree of 4. So you'd write degree is 4. And I suggest you guys memorize this because on the test, pretty sure you're not going to get this sheet. It's good to know. Memorize for each degree what it is. So, you know, degree 1 is linear, when degree 2 is quadratic, obviously the basics, but just knowing this will help. Okay, you can start go.
Yeah, whenever.
Is it recording?
Yeah.
Second floor.
So moving on to example number 2. Determine the end behaviors from the functions in example 1. So as you can see, the first function is negative x cubed. So what you would write is the end behavior as x approaches. So if we're doing it where x approaches the positive infinity, for this function, you go back to your notes and you see that as x approaches positive infinity, y approaches negative infinity. So as you would write, as x approaches positive infinity, comma, y approaches negative infinity. And if it was the other way around, to where the end behavior is going to negative infinity, you would write also as x approaches negative infinity. And going back to your notes, you can see that y goes up to the positive infinity. So you would write y goes to positive infinity. And if you were to write this in quadrant form, you can see that says goes from quadrant 2 to 4, and you can see in this rough sketch from quadrant 2 to 4. So you just write in brackets, I'll just put it here, from quadrant 2 to quadrant 4. Moving on to the next one, B, 7x. It's a positive odd degree function. So I'll just write again the end behavior as x approaches. So as x approaches a positive infinity, going back to your notes again, you would see that for a positive function with an odd degree, as x approaches a positive infinity, y also approaches the positive infinity. So you would write y approaches positive infinity. And say x is going on to the negative infinity, so you would write also as x approaches negative infinity, y approaches, looking back at your notes, you can see that it says as x goes to negative infinity, y also goes to negative infinity. So you write y goes to negative infinity. And if you were to write this in quadrant form, you would write it goes from quadrant 3 to 1, as you can see right here. And looking back at the graph, you can see it goes from quadrant 3 to 1. So you just write quadrant 3 to quadrant 1. Alright, last but not least, we have negative x to the power of 4. So you would write the end behavior as x approaches positive infinity. Referring back to your notes, you can see that negative function with an even degree as x approaches the positive infinity, y goes down to the negative infinity. So you'd write y approaches negative infinity. So now you would want to know what happens when x goes to the negative infinity. So you write also as x approaches negative infinity, y approaches, referring back to your notes again, you can see that it approaches the negative infinity also. So you write y approaches negative infinity. And if you write this in quadrant form, you can see that it goes from quadrant 3 to quadrant 4, as shown in my example right here. So you write in brackets quadrant 3 to quadrant 4. So moving on to example number 3, it asks you to give an example of a function that goes from quadrant 3 to quadrant 1. So looking back at your notes, you look for something that says it goes from quadrant 3 to 1. So it's not an even degree function. So it is a positive function with an odd degree. So you could write something like y equals x, or y equals x cubed. Yeah, because since they're both positive and odd degree, it works for this. Alright, so moving on to B, it's asking you to give an example of a function that goes from positive infinity to positive infinity. So as x approaches positive infinity, y also approaches positive infinity. So referring back to your notes, looking for where it goes off to positive infinity, you can see that for a positive function with an even degree, the end behavior is as x approaches positive infinity, y also approaches positive infinity. So you can write something along the lines of y equals x to the power of 4, or even y equals x squared. Going on to C, last question for this. A function that goes from quadrant 3 to 4. So I would look back here, nothing here. So right here, it says for a negative function with an even degree. So I could say something like y equals negative x squared, or even y equals negative x cubed, x to the power of 4. As long as it's a negative function with an even degree, it follows this. Alright, so now moving on to example 4. Which of the functions from example 3 use point symmetry? So you know that odd degree functions use point symmetry. As I bring back the notes, odd degree power functions use point or rotational symmetry. So looking back at example 3 for odd degree functions, you can see there's only two, y equals x and y equals x cubed. So you would write both y equals x and y equals x cubed use point symmetry. Please tell me I spell symmetry right. Okay, that's symmetry. Since they are odd degree functions. Alright, so this is the last question, example number 5. It's a problem-solving question. The surface area of a basketball is given by the function b of r equals 4 pi r squared, where r is the radius of the basketball in centimeters, and r equals all numbers is from 0 to 12. So RER, this is the domain. The domain is technically going from 0 to 12. So you want to find the b values from 0 to 12. So the first question is asking you graph BR. So you probably want to do a table of values and plug in numbers into this equation. So since it's going from 0 to 12, if I plugged in numbers, say I plugged in 4, second f pi, bracket 0, r0, squared, I obviously get 0. So I would put right here 0, 0. If you keep going, I could do it again. 4, second of pi. Now I go to 1. So bracket 1 squared equals 12.56. I round to the nearest decimal place, 6. You keep going and you end up with these values. So as you can see, I have it graphed here. I put for you guys the same exact graph. You guys just had to plot the points and draw it out. But as you can see from this table of values that I did from 0 to 12, I graphed it until 12. It's up to 12. Don't mind this. It's going up this way. It doesn't go down to negative. It keeps increasing, as you can see. So now for B, it says state the domain and range of the function. So B. So as you can see, even using the table of values, you can see it gives you in the question either way. The domain, it says R goes from 0 to 12, and R, is the domain. And as you can see here, it goes to 12. So you would write D equals bracket, don't mind the bracket, 0 is less than or equal to R, which is less than or equal to 12 R E R. And now moving on to the range of the function, you put R equals, and you go to the table of values, and as you can see here, R goes from 0 to 1809.6, and if you look back at the graph, from 0 to, you won't notice it here, but you have the table of values to 1809.6. So you would write, it goes from 0, so 0 is less than or equal to B, which is less than or equal to 1809.6 B E E R. Alright, so moving on to the final question, C. It says describe the similarities and differences between the graphs of BR, which is this, and y equals x squared, which is just like something like this. So I would write, so C, so similarity, I'll state the similarities first. So some similarities between this function 4 pi r squared and x squared is that they're both quadratic. They both have a degree of 2. So I can write both are quadratic with end behaviors from quadrant. Well, it's actually not. It's actually headed to quadrant 1 since this has a domain. So with n behaviors to quadrant 1. Since 4 pi r squared has starts from 0, so you cannot say it starts at quadrant 2 because it technically starts at quadrant 1 and ends there. It doesn't go anywhere else, so that's what you would write. They both also have positive leading coefficients. They both also have positive leading coefficients, which make them similar. Y equals x squared, y equals x squared, and b of r equals 4 pi r squared. So they both have positive leading coefficients. And if I were to plug in 0 into here, 0 squared is 0, so I'll get 0, 0. Same thing with plugging 0 into 4 pi r squared, it would be 0, 0. So I can say that they both have the same x and y intercept at 0 and 0, which make them similar. So now moving on to differences. So what's different about these two equations? So b of r equals 4 pi r squared has a restricted domain. As I said, it goes from 0 to 12. And y equals x squared does not have a restricted domain. It just goes on. It's just XER. So this means it also has a restricted range, as I'll show you right now. As you can see here, for 4 pi r squared, the domain is restricted, so is the range. As for normal quadratic functions, if I can just find my notes, as you can see in my notes that I wrote down that for both even and odd degree functions, domain is XER, and for the range of an even degree function with a positive leading coefficient, it's greater than 0. But here, it is greater than 0, but it's restricted, as you can see. B of r equals 4 pi r squared also has a vertical stretch, unlike y equals x squared. So I would write the function also has a vertical stretch by a factor of 4 pi right here, unlike y equals x squared, since it's just 1, a is 1, and for this a is 4 pi, which means it has a stretch. That means the 4 pi affects all the other points other than 0, 0, which means therefore there should be one word, therefore the points are different other than 0, 0. So when I say that all the points are different other than 0, 0, I mean, so if I plugged in for this, y equals, so I say I plugged in 1 for x, 1 squared, y would equal 1. And if I plugged in 1 in here, the 4 pi r squared, it will give me 12.6. So that's one point that's different. If I do it again, so for 2, when it's plugged into 4 pi r squared, it gives you 50.3. Whereas if I plugged it into x squared, it would give me y equals 4. Another point that's different. That's why I said the only points that are different, the only points that are the same is 0, 0, because when I plug in 0 in this, it's just 0, and same for here, it's just 0. And yeah, that concludes 1.1. I suggest you start your homework and make sure you kind of understand, all this, because on quizzes and tests, you won't be able to refer back to your notes. And yeah, that's it.